we've been studying functions for a while now and the derivatives of those functions, but not every graph can be represented as a function. So let's take a look at something really basic to illustrate this idea. So let's say for some reason, we're taking a look at the graph of this relation, and we're going to call this x squared over 9 plus y squared over 4 is going to be equal to 1. And the question is, well, what is the graph of this thing, right? Well, from pre-calculus, you may remember that you can go through and substitute 0 back in for y. So what happens when y is 0? Well, that means something squared divided by 9 has to be equal to 1. And so that's going to be plus or minus 3. So we have a negative 3 and we have a positive 3. Right? And now what happens when x is 0? Well, that means that something squared over 4 is 1, and we know 2 squared over 4 is 1, and also negative 2. So we get this, which is positive 2 and negative 2. And what do we end up with? Well, as best as I can draw it, it's not really a good drawing, but this is an ellipse, right? This is not a function now, right? Remember, a function has to pass the vertical line test, and that clearly does not pass the vertical line test. So that's what we call a relationship. However, we do know that there's a slope right here, and we could try to find an equation of a tangent line. And there's a slope over here. It's not the same one, right? There's even a slope right here. All right. And so the question is, how can we find the slopes on these sorts of graphs of relations but not functions? Because now we have two variables. All right. Now, and moreover, what if we can't solve for one of the variables? All right, it is feasible that we could solve this for y. We'd still get a really tricky function to try to find the derivative of. We probably have to use a chain rule in there, and it just becomes messy. So when this happens, when we have two variables, and we can't isolate one of the variables nicely, we use this idea of implicit differentiation. Implicit differentiation is used when we can't isolate, so we can't solve for one variable. Okay. And in other words, we can't necessarily, and I'm going to insert nicely. Right? And another thing that we have to consider is that the graph does not produce a function. The graph may not produce a function. So for instance, circles, ellipses, and there's a whole slew of other relations that aren't functions. So how do we do this? Well, what we can do very easily is we're just going to take the derivative of all the different terms, and anything that has a y in it, we're going to multiply by dy dx. Okay, so we're going to derive, as usual, all the terms. Okay, but if the term contains a y, then we multiply that term by dy dx. All right, it's actually a pretty simplistic process. And then finally, what we're going to do is at the end, we're going to solve for dy dx. All right, that's how we can do implicit. That's how we can try to find an implicit derivative. All right, so they are generally, students don't like these, and they are a little bit more algebraically taxing than some of the other derivatives that we found. Doesn't mean they're too tough, it just means that we have to do a little bit more work. Let's start off with a really easy example. This one we're not asking to find a specific slope, but we're just asking to find dy dx. Now, one way to be able to find dy dx, all right, and don't write this down or don't copy it, but we could solve this for y, couldn't we? Couldn't we subtract 5 from both sides? So we get sine y is x minus 5, and then we could take the arc sine of both sides. And then we can go through and just take the derivative of that. But the problem is that we don't know yet how to take the derivative of an arc function. All right, that's actually a little bit later in the course, not too much later. So let's scrap this, and let's see if we can do it a little bit easier by using implicit differentiation. Derivative of sine, cosine of y. Derivative of 5 is 0. Derivative of x is 1. However, anytime we take a derivative with respect to y, what we're going to do is we're going to multiply by dy dx. Right? So really nice and easy. So that's the only trick that we're doing now that's new. We can rewrite this to solve. So we've gone through and done step 1. Now we're going to solve for dy dx. So another way to write this would be cos y dy dx is equal to 1. We could divide both sides by the cosine of y. So dy dx equals 1 over cosine of y. Or we might remember from trigonometry that the reciprocal identity for cosine is going to be the secant of y. So that's our derivative of this function. It's just secant of y. Another example, and this one's a little bit more specific because it asks us to first of all find the slope, or find the implicit derivative of this relation, and then to find the slope at the given point. All right, so let's go ahead and do this. So we're going to take care of business as normal. Derivative of x cubed, 3x squared. Derivative of y cubed is going to be 3y squared. Derivative of negative 65 is 0. However, we can't forget that because we took the derivative with respect to y, we're now going to multiply by dy dx. Right? It's that easy. Now we solve for dy dx. We're just going to jump that 3x squared to the other side. So we get 3y squared dy dx is going to be equal to negative 3x squared. And then we're going to divide both sides by 3y squared. Now the 3's are going to cancel out, obviously. And the 3y squares are going to cancel out. So what are we left with? We're left with the slope anywhere on that relation, dy dx, is going to be equal to x squared over y squared, negative. Right? So that's part A that we were asked to do. Part A asked us to be able to find the implicit derivative. But it doesn't help us to find the rest of this yet. Okay, well, it does help us, excuse me, but we haven't answered it. So now we have to find the slope at the given point at 4, negative 1. So what we're going to do is we're going to substitute negative 1 in for x, and then negative 4 in for x, and negative 1 in for y. So we're going to say that this is dy dx at the point negative 4, 1, negative 4, negative 1, and that's going to be equal to the opposite of negative 4 squared divided by negative 1 squared. And now it's just a game of computation. We know this is negative from right here. Now 4 squared is 16, negative 1 squared is 1, and finally, by multivariable numerical methods, the opposite of 16 over 1 is negative 16, and this is part B. All right, so this is actually really cool because now we can find the slope at any point on one of these types of curves that's not necessarily a function. All right, and what I'm going to try to do is I'm going to try to graph this just to illustrate what this relation might look like, so that way we can kind of get an idea of what these different shapes are implicitly. Right. So hopefully this helps out a little bit. Now, make sure before you go on to the next video that you feel comfortable with this concept, because then we're going to start throwing in some of those other rules like product rule, chain rule, quotient rule to be able to find these implicit derivatives.